All right, folks, we are looking at a homework review 521. And with this one, we're still looking at rotations, reflections, translations. And our first question here is, in a rotation of a set of points, okay, so we're doing a rotation around the origin or some point. What geometric structures define the motion of the points? All right, so let's look at this a little closer. And if I have, let's say, we're going to rotate around the origin, and we have this point right here. Let's actually put it on some place easier. So if I have this point right here, and let's say that's at 1, 0. If we do a rotation of, let's say, 90 degrees, we know that this xy is actually going to be translated, or sorry, rotated, so we end up with the point negative yx, okay? So this is kind of like the math. This is something we did last week as well. Remember, we had to convert the points. Let's see what happens here. So if I have 1, 0, that's going to end up being 0, 1. So we're going to rotate. That's really not that great. And end up right here, okay? So what kind of, if we look back at what the question was, I look back here. In a rotation set of points, what geometric structure defines the motion of the points? Defines the motion of the points. So looking at that, the motion of the points, come on, share, boom. All right, the motion of the point, okay? If I was moving a number of points, rotating it, it would be the same thing. But here, if I rotate this point 90 degrees, we end up with this arc length, okay? So we're going to end up with an arc. And with that, since we're going to end up with an arc, 1 second here. Ugh. Whatever. Okay, so since we're going to end up with an arc, it's going to actually be a circular arc, okay? If I was rotating this point around, it still ends up being like an arc, okay? So around the center, so we're going about the origin. About means around, about the origin. Okay, and that is number 1. All right, so now we're on number 2. What linear relationship defines the movement of a translation? So again, a translation, just think of it this way. A translation is just like, different words for the same object in different languages. You translate it, it's the same shape, it's just been translated, it's been moved to another language, it's been moved to another position. So if I was translating this up and to the right, and I don't need to exactly have the exact points here, I'm just gonna show you, like, this is a translation that occurred. I'm going up and to the right to get this new image from my pre-image. What path did the vertexes here, 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 what path did they take to get to the new image? Remember, this is the image, and this is the pre-image, okay? Just remember that since we're translating it, the pre is where it comes from, the image is where it results. And if you look at this, it's pretty straightforward, because look, we end up with, if I could draw straight, we end up with parallel lines. Okay, and I think the main hard problem about this, the main hard part of this problem is just knowing the vocabulary you can use to it. So if you're not sure about that, maybe it's time to check over those con videos again. Okay, that's number 2. All right, number 3. What linear relationship defines the movement of a reflection? Now, these are worded very challenged. This is a challenge here. So, don't worry if you're not sure and you need some help with this. So what is the relationship of a point that is reflected? So if we look at this, here's my situation. And I'll write it in black here. We got this line here, y is equal to x. That's our basic line. X equal to y. Doesn't matter. I'll make a y is equal to x. Okay. So this is our basic line. It goes at 45 degrees. When x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3, and so on. Okay, so if we're doing a reflection across this line, the main thing here is the reflection is going to be on the other side of this line, and it's going to be here if it's the same distance apart, it's the same distance up and over because it's reflected, right? So instead of 3, -3, 3, -3, it's going to be over here at -3, 3. Okay. So when you have a reflection, that's how the points are going to correspond. You can think of it like you can go, what is that step, and then 90 degrees to get to the other. The main thing here is that when we are doing a reflection, the point is reflected about the line, and it is perpendicular to the line. Okay, so just think if we had this point here, right? If I reflect it across, you can't even see that. I don't know if you can see that. If I had this point here, it's reflected across the y-axis, right? It's not going to be reflected and then end up down here, right? A reflection is going to be directly reflected. It's going to be reflected at a degree measurement of 90 degrees from the line that we're translating across. Excuse me, reflecting across. That's a tricky one. These are conceptual problems, so don't worry too much. Let's keep on going. Don't stop. All right, we're on number 4. In a rotation, what point is moved the greatest distance? Okay, so I want you to think about this. Think about this. If, let's say this. All right, and this will give me a chance to draw. I like drawing. So anybody ever been to, and I'm talking to you already. Anyone ever been to, like Knott's Berry Farm or Disneyland, where they, I don't know if they have at Disneyland, but where they have like a swing, right? And everyone is, the centrifugal force, makes you, this is like the swing, here's the ride, and you wait in line right here, here's the gate. Don't go in while it's moving. All right. So if we, as number 4, if we were on the swing ride, right? And I was looking down on it, it would look like, here's the top of the ride, right? And there would be, people on swings out here because the centrifugal force spins you around, okay? So, and you could be right next to somebody, you can be holding hands, your sweetheart, you can be holding hands, and the person on the outside is going to be represented here by our black marked areas here. And the people that were swinging on the inside, their little carriage starts and is connected to the ride further in, right? It's further in. So we could see here that if you are on the outside, right? If you're on the outside spinning around the center of this mechanism, you are going to travel further. You're going to travel further because your seat is further out. You can think of it like if you run track, this is the reason why they stagger start, because you're running around a track and the person on the inside has less distance to run, right? This distance is less than this distance, okay? So the question was asking, what point travels the furthest within a rotation? It's gonna be the point that is furthest from the center of rotation. So it's gonna be the point furthest from center of rotation, okay? That's the key thing here. And think of like the track model, think about the swing model, and I think that should probably help us. All right. One more and then we'll have, all right, number 5, it's gonna be the last exercise for this video. All right, in a reflection, what happens to the point that lies on the line of reflection? All right, so there's a couple ideas here. First, we have to remember what a reflection is. So I think of a reflection, just, reflection in a mirror. So if I had this point here and I was reflecting across x is equal to 0, right? It's going to end up being over on this side, okay? So that's it, the point, and these are going to be the same distance from our line of symmetry here. But here's the thing. If the point is on on the line of symmetry. You could think of it as if you folded a piece of paper, right? And the point is in the crease, it doesn't move. This point right here isn't going to move to the left or right because look, it's reflected across this line and the point is on the line. Let me see. Okay, great. So this is my US Census. I got it in the mail, right? If we were doing a reflection, right? Reflecting this point across the y-axis, the crease here. You know, if I was here, it would end up being over here, over here. But look, if I say that my point is here, the number, 0 here on 2020, if I fold this over, well, it's not exactly on the front, but like at the very bottom of that 0. If I fold it over, look, it doesn't move. It doesn't move. So when you have a point that is on the crease, that is on the line of reflection, that point does not move. Okay, it remains stagnant. It is rigid. All right, that's it for this grouping of problems. Check out my other video I'm going to make right now for the rest of the problems here. All right.